Ladies and gentlemen, welcome to the Mettler Toledo webinar on Materials Characterization by Thermal Analysis. Materials characterization is necessary for the study and development of new materials. Thermal analysis techniques provide valuable information on the thermal properties of materials and are relatively simple compared with many alternative methods. This webinar is aimed at getting you familiarized with thermal analysis in general and demonstrates the common uses of thermal analysis techniques in various industries with a number of interesting application examples. This slide summarizes the main topics covered in this seminar. I would like to begin with a general introduction to thermal analysis, where I describe its various applications in different fields. I will then discuss the most important techniques used in thermal analysis. These are differential scanning calorimetry, or DSC, thermo-optical analysis, or TOA, thermogravimetric analysis, or TGA, thermomechanical analysis, or TMA, and dynamic mechanical analysis, or DMA. I will provide more detail about these techniques later on, using numerous application examples. The seminar will conclude with a summary of the main techniques and applications discussed, along with a list of useful material to further educate yourself on almost any topic related to thermal analysis and its techniques for a diverse range of industries and applications. Quality is an important factor for consumers when deciding whether or not to make a purchase. On the left, we see a happy customer sitting comfortably in a good quality chair. On the right, however, a fault in the manufacturing process resulted in product failure with serious consequences. In this case, key bearings in the chair failed, causing it to collapse. Such defects are costly, harming both the consumer and the reputation of the manufacturer. So, how can a product fail? Most often, product failures are related to design errors, poor quality or unsuitable materials, incorrect material processing, or manufacturing errors. For these reasons, it is vital to determine whether a material exhibits the correct properties for its intended use. Only then can proper materials be selected and the necessary production processes optimized. Typical examples include the identification of polymers by their glass transition temperature, crystallization and melting temperatures, composition analysis, and decomposition behavior, or the determination of mechanical parameters, such as the coefficient of thermal expansion or the modulus. Where can thermal analysis be used? Quality control, R&D, and failure analysis are areas in which thermal analysis makes a significant contribution. In quality control, raw materials or final products must be verified to ensure they meet predefined specifications, for example for purity, composition, mechanical strength, and crystallinity, to name just a few. R&D places emphasis on the development of new materials and the optimization of processing procedures for existing materials. This requires extensive study into the characteristics of new, substitute, and modified materials. Existing materials may also need to be evaluated when new production methods are introduced. Quite often, materials fail in their daily use. This slide shows an example of a material used to make a high-temperature resistant seal. The working temperature range should lie between room temperature and 200 degrees Celsius. However, it was found that some of the seals failed when heated to a temperature higher than 170 degrees Celsius. A DSC experiment was devised to identify the cause behind such failures. Curves for good and bad seals are shown in the diagram on the slide. It can be observed that the good seal material undergoes a small glass transition at around 150 degrees Celsius, followed by melting, which peaks at approximately 340 degrees Celsius. From this, we can conclude that most of the material is available in crystalline form. The bad material, however, shows a similar magnitude in the delta Cp value, but this is followed by an exothermic peak due to partial crystallization. The melting peak of both samples is identical. The bad material exhibited much lower crystallinity than the good material, since the former was cooled too fast, preventing complete crystallization. During crystallization, the material shrinks. This is the reason for the bad seals failing. In this example, the cooling conditions required for complete crystallization can be studied by DSC. DSC can also be used to optimize the processing conditions for the production of such seals. But let's start at the beginning. What exactly is thermal analysis? The ICTAC definition of thermal analysis is a group of techniques in which a physical property of a substance is measured as a function of temperature, while the substance is subjected to a controlled temperature program. The schematic diagram on the right shows a simple temperature program with isothermal and linear segments. The bottom part of the slide illustrates typical thermal events and processes that occur when a sample is heated. For example, the melting process, during which a sample transitions from a solid to liquid state, and oxidation, where a sample exposed to air or oxygen will start to oxidize and finally decompose. The oxidation induction time or temperature, OIT for short, can be determined in an oxygen atmosphere. OIT is a commonly used parameter for characterizing the stability of oils and polymers. Thermal analysis techniques are used to investigate all of these effects. This slide shows the most important techniques used in thermal analysis, namely differential scanning calorimetry, or DSC. This is the most widely used thermal analysis technique. The picture shows a DSC sensor with a sample, colored red, and reference crucible. Thermo-optical analysis, or TOA. This technique allows you to visually follow changes in your sample, which is placed in a hot stage and mounted on a microscope. Thermogravimetric analysis, or TGA. This technique measures the mass of a sample as a function of temperature using a highly sensitive balance. Thermomechanical analysis, or TMA. Here we see the sample, colored red, positioned between the fixed and moving quartz probes. And finally, dynamic mechanical analysis, or DMA. The picture shows one of the several available clamping assemblies, in this case, compression mode. I will explain these techniques in more detail in the following slides, which also include examples of useful applications. The table lists the most important industries for thermal analysis and their corresponding applications. For instance, knowledge of melting and crystallization behavior is important for identifying materials in the plastics industry. For thermosets or adhesives, gelation or curing times at different temperatures are critical parameters that affect their daily use. Elastomers or rubbers are widely used in many sectors, such as the automotive industry for the manufacturing of tires, hoses, and suspension components, as well as the construction industry for sealing materials, bridge bearings, and damping materials. The main properties investigated are glass transition, composition, expansion, the modulus, and damping and creep behavior. The food, pharmaceutical, and cosmetic industries have many common thermal analysis applications, including the investigation of polymorphism, the property allowing a material to exist in different crystalline forms with varying moisture content and structural stability. This is particularly important for shelf life and determining storage conditions. I will now discuss the different thermal analysis techniques in some more detail. Let us begin with DSC. This technique allows us to determine the energy absorbed or released by a sample as it is heated or cooled. There are several different types of DSC instruments. The standard Mettler Toledo DSC measures samples from -150 degrees Celsius to +700 degrees Celsius at heating rates of up to 300 Kelvin per minute. The samples are normally measured in small crucibles made of aluminum, alumina, or other materials using 1 to 20 milligrams of sample material. The Mettler Toledo Flash DSC expands the maximum heating rate to 2,400,000 Kelvin per minute and the cooling rate to 240,000 Kelvin per minute. To achieve this, the Flash DSC-1 uses very small samples weighing about 100 nanograms and no sample crucibles, as the sample is placed directly onto the chip sensor. The ultra-fast heating and cooling rates allow industrial process conditions to be simulated where materials frequently undergo extremely rapid cooling rates. Another powerful DSC technique is high-pressure DSC, or HPDSC for short. The Mettler Toledo HPDSC can analyze samples exposed to inert gas or reactive gas atmospheres and at pressures of up to 100 bar or 10 megapascals. This suppresses undesired vaporization and enables the stability of samples to be studied, for example, at increased oxygen pressures. The schematic curve on the left shows a typical DSC measurement curve of a semi-crystalline polymer. Exothermic events point in the upward direction, and endothermic events downwards. Each event is numbered next to the curve. 1. The initial deflection or startup transient of the DSC due to sample and crucible heat capacity. 2. Is the baseline where no thermal effects occur. 3 is a glass transition with enthalpy relaxation. 4 is cold crystallization. 5 is melting of the crystalline fraction. And finally, 6 is exothermic oxidative decomposition. The table on the left of the slide summarizes the most common analytical applications for which DSC is employed. DSC is used to investigate effects and processes such as glass transitions, melting, crystallization, chemical reactions, and thermal stability. All of these events involve an enthalpy change, which is readily observed by DSC. The information obtained can be used to identify polymers, investigate the working range of materials, and for compositional analysis. Suitable methods can easily be developed for quality control and for the analysis of raw materials, additives, and fillers. Finally, the technique can also be used to evaluate vulcanization and other reactions. DSC curves also contain information about the thermal history of a sample, for example, aging. The stability of materials can be determined using the oxidation induction time, or OIT for short. Other important applications include investigating curing kinetics of reactive systems or the influence of stabilizers, plasticizers, or other additives. Most of these events demonstrate enthalpy changes that occur when the temperature is increased or decreased. The picture on the right-hand side offers a view of an open DSC furnace with samples and reference crucibles. The standard crucibles are made of aluminum. Mettler Toledo has also developed versatile optical techniques that allow you to observe changes that occur in a sample while it is heated or cooled. The techniques include DSC microscopy and DSC chemiluminescence. The photocalorimetry option is used in combination with the DSC and allows the study of the curing process for adhesives or paints under visible or UV light. The slide shows examples of polymer fingerprinting. The diagram displays the glass transition, melting, and crystallization curves of several commonly used polymers. Curves like these allow the identification of polymers and provide an easy way to compare different batches of the same material. Glass transitions and melting peaks are the most common effects measured. Quantitatively, a melting peak is characterized by its peak temperature and the enthalpy of melting. The normalized enthalpy for the melting of a sample can also be used to quantify its crystallinity if suitable reference materials or reference values are available. Glass transitions are characterized by a step-like change in the heat flow or enthalpy. In the first heating run, the transition is often accompanied by a peak related to enthalpy relaxation caused by aging. An example of this can be seen in the DSC curve of PET. Large enthalpy relaxation peaks only appear in the first heating run, as the heating erases the aging history. The temperatures at which glass transition and melting occur define the usable temperature range for manufactured parts. Crystallization is normally measured during cooling of the sample from the melt. The DSC curves of two PBT samples, see bottom of graph, illustrate the effect of additives on the crystallization behavior. In this case, carbon black, which is used as a colorant and UV stabilizer. Another important application for differential scanning calorimetry is to measure the curing reaction in thermosetting materials. The diagram displays the DSC curves of 3 samples that were cured to different extents. The results show that with an increasing degree of cure, the glass transition shifts to higher temperatures, and the enthalpy of the post-curing reaction decreases. In the diagram, the degree of cure increases from top to bottom, starting with the blue curve of the uncured sample to the black curve of the fully cured sample. If the reaction enthalpy of the uncured material is known, the degree of conversion before the measurement can be calculated from the enthalpy of the post-curing reaction. Many materials, such as polymers, oils, or food, start to degrade after a certain time when exposed to oxygen. The oxidation-induction time test is frequently used to characterize the oxidation stability of materials. Detailed procedures are defined in various ASTM and ISO methods. The general method used for such experiments is shown by the blue curve in this slide. Initially, the test specimen is rapidly heated in an inert atmosphere to a temperature at which the oxidation is expected to occur within a reasonable amount of time, typically 30 minutes. An equilibration time at this temperature ensures thermal equilibrium before the atmosphere is changed to oxygen or air. The oxidation induction time, or OIT for short, is the time it takes until oxidation begins. This is detected as an exothermic upturn of the heat flow, and the time is measured from the intersection of the tangents before and after the event. The OIT is directly related to the relative stability of a material at a particular temperature. In the example shown here, OIT measurements were performed at 210 degrees Celsius on polyethylene tubing, which had been exposed to flowing aqueous solutions of chemicals for some time. 2 test specimens, one from the outer and the other from the inner side of the tubing, had their respective OIT evaluated. The test specimen originating from the inner side of the tubing is denoted as stressed, and the test specimen originating from the outer side of the tubing as unstressed. Their DSC curves are shown in red and black, respectively. The dramatic decrease in the OIT value obtained for the stressed sample shows the damage caused by the chemicals transported in the tubing. Since the OIT measurement temperature is usually far above the temperature at which the material is normally used, OIT experiments are known as accelerated aging tests. The method is frequently used to study the influence of antioxidants or other stabilizers on the stability of a material. In the absence of any additives, information can be obtained on comparative molecular weights. The larger the OIT value, the higher the molecular weight. Polymorphism is the ability of a single material to exist in different crystalline structures. This is of particular interest for foodstuffs and pharmaceuticals, where the bioavailability of, for example, a drug depends on the structure of the active pharmaceutical ingredient. DSC is a simple and quick screening tool to identify the presence of different polymorphs. The example shown here presents the heating curves of sulfapyridine, which is used for its antibacterial effects. The sample was first heated to 200 degrees Celsius. See the blue curve. The sharp endothermic peak at around 190 degrees Celsius indicates the melting of the stable structure. After heating, the melt was shock-cooled by simply placing the sample pan with the sample robot onto the turntable of the sample robot. The second heating run, shown by the red curve, first shows a glass transition. This tells us that the sample did not crystallize during cooling. The glass transition is followed by an exothermic cold crystallization. The crystals formed are partially metastable. The metastable crystals transform to a more stable modification through an exothermic monotropic solid-solid transition at around 120 degrees Celsius. This modification then melts at 179 degrees Celsius. Part of the molten crystals then crystallize into the most stable phase, which finally melts at 190 degrees Celsius. To discover the different polymorphs of a material, one has to heat and cool the sample at different heating and cooling rates. The appearance of different melting peaks is characteristic of a sample exhibiting polymorphism. The next slide shows an application example involving the use of an ultra-fast scanning DSC instrument, the Flash DSC-1. This instrument allows measurements to be made at heating rates of up to 2,400,000 Kelvin per minute and at cooling rates of up to 200,000 Kelvin per minute. To achieve this, the Flash DSC-1 requires a typical sample mass of a few hundred nanograms. The tiny samples are put directly on the chip sensor, which is mounted into the Flash DSC. If a semi-crystalline polymer is measured with a conventional DSC instrument, the DSC curves generally exhibit a glass transition whose step height is proportional to the amorphous material content, and an endothermic peak, which is related to the melting of the crystalline component. In some materials, an exothermic event known as cold crystallization can occur between the glass transition and the melting peak. Cold crystallization is a reorganizational process which changes the structure of the material. Consequently, the structure of the sample may be changed during heating from the glass transition onwards. In other words, what is measured as a melting peak is not necessarily representative of the original structure of the sample. If one is interested in the original structure of a material, one has to heat up a test specimen at a heating rate high enough to prevent such reorganization. This minimum heating rate will depend on the material and can only be determined experimentally. The slide illustrates a reorganization process using isotactic polypropylene. The test specimen has been cooled from the melt at a cooling rate of 4,000 degrees per second before each heating measurement. With this cooling rate, crystallization is suppressed, resulting in a fully amorphous test specimen. Each curve represents a heating run performed at the indicated heating rate. The glass transition appears as a step at about 0 degrees Celsius. This is immediately followed by an exothermic peak, which we attribute to the cold crystallization. This peak is sensitive to the heating rate, increasing from about 20 to 80 degrees Celsius for the rates shown. Before the melting process, we find another small exothermic peak, which represents a reorganization process. It can be seen that all these effects depend on the heating rate. Only at heating rates above 20,000 Kelvin per second is reorganization completely suppressed. Therefore, in order to study the original structure of an IPP sample, it is imperative to use heating rates of at least 20,000 Kelvin per second. Now let us turn our attention to thermo-optical analysis, or TOA. TOA is performed by using a hot stage mounted on a microscope, as shown on this slide. A hot stage is a special cell into which a sample is inserted on a slide and is then heated or cooled or held at constant temperature. During the temperature program, images of the sample are continuously captured in transmission using a suitable camera. Processes such as decomposition, solid-solid transitions, and melting or crystallization can then be observed in situ. Polarized light is often used to improve the images of crystals. Thermo-optical analysis is particularly useful when investigating the shrinkage, for example, of fibers, crystallization during heating, cooling, or under isothermal conditions, polymorphism, melting, and thermal stability, as it affords unique insight into these processes, as we shall see in the next slide. In this slide, we illustrate the use of hot stage microscopy with a sulfopyridine sample as demonstrated in the DSC curve in a previous slide. From the DSC experiment, we suspect polymorphism. This is confirmed by using a hot stage with image capture of the different crystalline forms. For the hot stage experiment, the sample was also quenched from the melt, and the initial heating rate was the same as for the DSC experiment. Some images recorded at selected temperatures during heating are shown together with the respective DSC curve. The images were obtained using polarized light. The image recorded at 120 degrees Celsius shows that during the cold crystallization, different types of crystals were formed. After the monotropic solid-solid transition, some new large crystals are present. The less stable crystals melt at around 175 degrees Celsius. A part of the melt crystallizes to the most stable crystals. The stable crystals finally melt at around 192 degrees Celsius. Now let us move on to thermogravimetric analysis, or TGA. In this technique, the mass of a sample is continuously measured as it is heated in a defined atmosphere. We simply put a few milligrams of sample into a crucible, heat it, and continuously record the mass change. This allows us to obtain information on the composition of the sample. The schematic curve on the left shows a typical TGA measurement curve of a polymer. The different effects are numbered next to the curve and explained in the table. These are 1. Heating begins and volatile components such as moisture and solvent residues vaporize. 2. Decomposition of the polymer. 3. The atmosphere is switched from nitrogen to air. 4. The carbon black burns. 5. A residue consisting of ash, fillers, glass fibers, etc. remains behind. The picture on the right shows a view of the open furnace of a TGA DSC instrument, emphasizing the sample holder with positions for the sample and reference crucibles. The standard crucibles are made of alumina. The table on the left side of the slide summarizes the main analytical applications of TGA. TGA is used to investigate processes such as vaporization or decomposition. It allows you to measure thermal stability, the kinetics of reactions, and reaction stoichiometry. The combination of TGA with a mass spectrometer, a Fourier transform infrared spectrometer, or a GC-MS system allows you to identify gaseous compounds evolved during the analysis. Mettler Toledo TGA-DSC instruments simultaneously measure the heat flow together with the weight change. This can be used to identify processes such as melting or solid-solid transitions that are not related to mass changes. Also, the DSC can be used to determine the specific heat capacity of a material at high temperatures. The first TGA application example shows the analysis of an elastomer or rubber material. The sample was first heated to 800 degrees under inert conditions. At 800 degrees, the atmosphere was switched from nitrogen to oxygen. The upper curve shows the weight trace, TGA, and the lower curve shows its first derivative. The first weight loss step, which is usually between room temperature and 300 degrees, comprises volatile components such as plasticizers, oils, moisture, or solvent residues. The sample then pyrolyzes in a single step. From this, we can conclude that the sample consists of a single polymer. Usually, loss of volatiles and depolymerization overlap. This can also be seen on the first derivative of the TGA curve in the lower curve. In order to get a better separation of the volatiles and the pyrolysis step, the TGA-DSC is operated at reduced pressure. At 800 degrees, the atmosphere was switched from nitrogen to air. This resulted in the combustion of the carbon black used as filler in the rubber. Finally, at 1000 degrees, inorganic components remain as a residue. Evaluation of the TGA curve yielded the following sample composition: 11.2% volatile components, 49.1% of polymer, and 35.9% of carbon black. The residue of about 3.2% includes some inorganic materials such as zinc oxide, used as catalysts for the vulcanization. The Mettler Toledo TGA-DSC instruments can simultaneously measure the heat flow originating from melting or decomposition reactions. This is illustrated in this slide. The simultaneous measurement of the heat flow also allows the detection of events that are not related to a mass change. Calcium carbonate is widely used as a filler in the polymer industry. Due to its hydrophilic nature, it is incompatible with some of the most common polymers, such as polyethylene and polypropylene. To ensure compatibility, calcium carbonate is frequently coated with stearic acid. Stearic acid forms a monolayered array of alkyl chains on the surface of calcium carbonate particles, oriented with the carboxylic groups adjacent to the calcium carbonate surface. With excess stearic acid, additional layers may be formed. A minimum amount of stearic acid is needed to ensure compatibility. With excessive amounts of stearic acid, the mechanical properties are affected and the cost is greater. Thus, the amount of stearic acid on the calcium carbonate particle's surface is crucial from both a technical and an economic standpoint. Using TGA, the amount of stearic acid on the calcium carbonate can be accurately determined. This is illustrated on the slide. The sample was heated in oxygen from room temperature to 400 degrees in an aluminum pan with a pierced lid. The upper curve is the TGA curve. Between room temperature and 180 degrees, a small mass loss of about 0.2% is measured. This can be attributed to the release of moisture or other volatiles. At higher temperatures, two distinct steps are observed, which are due to the oxidation of the second and the first layer of stearic acid. The total amount of stearic acid on the calcium carbonate is the sum of these two steps. In this example, this amounts to 1.48%. The DSC curve, simultaneously recorded with the TGA curve, is shown at the bottom of this slide. The oxidation behavior of the organic coating can be seen on the DSC curve as an exothermic peak. The oxidation onset temperature for the second layer starts at around 200 degrees, while the oxidation of the first layer occurs at about 250 degrees. With such experiments, the optimum amount of stearic acid coating for the calcium carbonate particles can be determined. The Mettler Toledo TGA DSCs can be interfaced with several evolved gas analyzers, such as a mass spectrometer, MS, Fourier transform infrared spectrometer, FTIR, or a combination of a gas chromatograph and a mass spectrometer. This allows the identification of released products and increases the power of TGA considerably. Such coupled systems are used in many fields, for example in the plastics, pharmaceutical, and rubber industries for the identification of decomposition products, additives, or solvents. Solvents are often used both for the synthesis of a pharmaceutical substance and for its purification or recrystallization. The unwanted presence of residual amounts of solvents in a drug has to be quantified and their concentration kept as low as possible. The slide shows the results of an experiment in which the residual solvents were identified in an active pharmaceutical ingredient by using the TGA-MS technique. The TGA curve exhibits several mass loss steps. In the final step, above 250 degrees, the substance starts to decompose. The two steps in the range of 120 degrees to 240 degrees indicate that moisture or solvents are lost through heating. The simultaneously recorded mass spectrometer ion curves show that the mass loss steps correspond to methanol and acetone. From the TGA experiment, one can therefore estimate that the sample contained around 2% and 5% of methanol and acetone, respectively. Such concentrations for acetone are unacceptable according to regulations. The manufacturing process therefore needs to be modified to bring the residual concentration of acetone within the specified limits. We now move on to thermomechanical analysis, or TMA. This technique measures the dimensional changes of a sample as it is heated or cooled. The schematic curve on the left shows the result from a typical TMA measurement on a sample mounted in compression with a small applied load. The effects are numbered next to the curve and explained in the table. 1 is the low rate of expansion below the glass transition. 2 is the glass transition temperature at which the rate of expansion increases. 3 is the higher rate of expansion above the glass transition. 4 is softening with plastic deformation under the influence of an applied load. The table on the left summarizes different analytical applications of TMA. TMA measures dimensional changes of a sample under a defined load. This information can be used to determine the coefficient of thermal expansion. Furthermore, other thermal effects such as glass transitions, melting, crystallization, polymorphism, curing, or swelling behavior can be investigated. Besides conventional TMA measurements, in which the load remains constant, dynamic load TMA or DLTMA can also be performed. This mode typically employs a periodic applied load with a constant amplitude, for example, plus and minus 1 Newton. If a sample hardens, as in the cure process, the measured displacement amplitude decreases markedly. This technique can be used to determine Young's modulus. The picture on the right shows a typical TMA configuration where a ballpoint probe is in contact with a blue sample resting on a flat support. The probe penetrates the sample as it softens. In the following slides, I will describe specific application examples. Materials expand or contract with changing temperature. Thermal expansion in a part containing multiple materials may result in cracks or failure of the component. Therefore, knowledge of the coefficient of thermal expansion, CTE, is an important requirement for preventing product failures. One major application of TMA is the determination of the coefficient of thermal expansion. This can be carried out for bulk materials as well as for thin films and fibers. The main diagram in this slide shows TMA curves for 3 different materials with increasing temperature. The smaller inset shows the coefficient of thermal expansion as a function of temperature. The materials include Invar, a nickel-steel alloy with 36% nickel, which has practically zero thermal expansion at ambient temperature. Duran glass, like most mineral glasses, has a very low coefficient of expansion below the glass transition temperature. Crystalline quartz, measured here in the C-axis direction, expands steadily up to the solid-solid transition at about 575 degrees Celsius, after which it begins to contract. An adhesive is shown initially in its liquid state. During isothermal cure, the viscosity of the adhesive increases as cure or cross-linking progresses. From a technical point of view, the so-called gel point or pot time is of major interest. It denotes the time at which the repositioning of parts in the evolved structure is no longer possible. To determine this gelation time, a dynamic load TMA or DLTMA has been used. In this mode, the sample is subjected to alternating forces. In the example, we were applying forces of plus minus 0.1 Newton. The respective force profile is shown in the upper right diagram. If the sample is still liquid, the probe lifts off the sample at the negative force. This explains the large displacement amplitude during the first 20 minutes of the experiment. With progressive curing, the viscosity of the sample increases and the samples become increasingly sticky. This reduces the displacement amplitude dramatically. When the sample is fully cured and the material is in a glassy state, the displacement amplitude is effectively given by the stiffness of the instrument, since the measurement probes become stuck together by the sample. The time at which the displacement amplitude starts to decrease corresponds to the gel point, or pot or gelation time. In the example, the gelation time at 10 degrees Celsius is about 26 minutes. Dynamic mechanical analysis measures a sample's response to deformation as a function of time, temperature, and/or frequency. The schematic diagram on the left shows the results obtained from a DMA shear measurement of a crash-cooled semi-crystalline polymer. The curves display the storage modulus, G', the loss modulus, G', and the loss factor, tan delta, as a function of temperature. The different events are numbered next to the curve and explained in the table. These are 1. Secondary relaxation, observed as a peak in the tan delta curve and a small drop in the storage modulus curve, G'. 2. The glass transition, seen as a reasonably large peak in the tan delta curve and as a decrease in the storage modulus curve, G'. 3. Cold crystallization of the polymer. The stiffness and hence the storage modulus, G', increase together with some activity in tan delta. 4. Recrystallization accompanied by a peak in tan delta and frequently a rise in G'. 5. Melting of the crystalline fraction with a drastic decrease in both the storage modulus, G', and loss modulus, G'. After melting, tan delta, or the loss factor, increases considerably. G' is then larger than G'. The table on the left lists the main analytical applications of DMA. In general, DMA provides information about relaxation processes, such as the glass transition or secondary relaxations. Curing processes, pot or gelation time, melting, and crystallization are other application possibilities that can be studied by DMA. DMA is also widely used in a humidity-controlled environment to study the effect of moisture on material properties. Quantitatively, DMA provides accurate data on the shear and Young's modulus as a function of temperature and frequency. Furthermore, the impact of the deformation amplitude or strain dependence on the modulus can be investigated. This is of particular importance for filled rubbers. The picture on the right shows a sample installed in the DMA in one of the bending modes. Nowadays, fiber-reinforced polymers are widely used, for instance, in the aviation and automotive industries. Such composite materials offer moduli and elasticities similar to metals and are considerably lighter. Furthermore, they can be shaped into almost any geometry. Such properties make composites a cost-effective solution for many applications. The slide shows the DMA curves of a glass fiber reinforced epoxy composite measured in single cantilever mode from -120 to 300 degrees Celsius. From top to bottom, the diagram shows the curves of the storage modulus G', loss modulus G', and the tan delta curve. The glass transition temperature limits the temperature range in which a composite can be used. DMA is the most sensitive method available for measuring glass transition, particularly in highly filled materials such as composites. In DMA, a step in the storage modulus and a peak in both the loss modulus and the tan delta curve characterize the glass transition, sometimes also called the alpha transition. The glass transition temperature is frequently characterized either by the onset temperature of the G' or by the peak temperatures of either the G' or tan delta curve. The three temperatures will always differ. Furthermore, the onset temperature of G' depends on the representation of the G' curve. If E' is displayed on a logarithmic scale, the onset temperature will generally be lower compared to a linear scale. Therefore, one usually prefers the inflection of G' curves, or peak temperatures in G' or tan delta, as characteristic temperatures for glass transition. Other than glass transition, or TG, other sub-TG relaxation processes, also known as secondary relaxations, can be seen by DMA. Such transitions are usually not detected by DSC. The highest temperature relaxation is typically referred to as the alpha relaxation, whereas lower temperature relaxations are named beta, gamma, and so on. The alpha relaxation is usually the glass transition process, while the lower temperature transitions involve more localized molecular deformations, either inside groups or the main chain. They always occur below the glass transition temperature. Similar to the glass transition temperature, they are characterized by a step-like change of the modulus and by frequency-dependent peaks on both the loss modulus and tan delta curves. They generally have a lower activation energy than the glass transition. The use of a multiple frequency thermal scan means that relaxations can easily be separated from other events, such as melting and water evaporation, since these exhibit no frequency dependence. Secondary relaxations play an important role in the impact resistance of materials. The mechanical properties of materials change with temperature and frequency. For many applications, this has a crucial bearing on their performance. Therefore, the frequency dependence of the modulus and damping, as seen by tan delta, are extremely important. For example, an adhesive must absorb stresses in spite of temperature fluctuations during day and night cycles, that is, low-frequency variations. However, the adhesive must also react elastically to short-term mechanical impacts, reflecting high-frequency variations. The slide shows a frequency sweep across the glass transition of a styrene butadiene rubber, or SBR for short. The measurement was performed isothermally at -10 degrees Celsius. The frequency ranges from 1 millihertz to 1 kilohertz. In this frequency range, G' changes by around 3 decades. The maximum value of tan delta is reached at about 0.3 Hz. At low frequency, the material is soft and behaves in a rubbery manner. As frequency increases, the material stiffens and becomes glassy. This demonstrates the ability of this material to behave like a rubber at frequencies in the millihertz range, and conversely, to behave in a glassy fashion at frequencies in the kilohertz range, while being held at the same temperature. Thermal analysis comprises a number of easy-to-use and powerful techniques for characterizing thermal properties of materials, such as those for thermoplastics, thermosets, elastomers, adhesives, chemicals, paints and lacquers, foodstuffs, pharmaceuticals, fats and oils, metals and ceramics. The table summarizes the most important events and properties that characterize materials, as well as the thermal analysis techniques recommended for their measurement. A red box means that the technique is strongly recommended. A blue box signifies that the technique can only be used in certain cases. The most important effects that can be analyzed by DSC are melting point, melting range, and melting behavior. DSC is also used to determine the heat of fusion, glass transition, and oxidation stability. TOA is useful to investigate polymorphic transition, overlapping effects such as melting with decomposition, and melting and crystallization behavior. TGA measures mass changes. The main applications of TGA are content determination, thermal stability, decomposition kinetics, and composition analysis. TMA is normally used to study the expansion, softening, or shrinkage of materials and the glass transition. Its unique application is the determination of the coefficient of thermal expansion, or CTE. DMA is used to measure the mechanical behavior and properties of materials. This includes the modulus and damping behavior. It is the most sensitive method for measuring and characterizing glass transitions, TG, and sub-TG relaxations in materials. This slide gives an overview of the temperature ranges available on Mettler Toledo DSC, TGA, TMA, DMA, and TOA instruments. Depending on the specific cooling accessories, DSC experiments can be performed at temperatures between minus 150 degrees Celsius and plus 700 degrees. TGA measurements normally begin at room temperature. The maximum possible temperature is 1,600 degrees Celsius. TMA experiments can be performed between minus 150 degrees and plus 1,100 degrees. DMA samples are measured in the range of minus 150 degrees to plus 600 degrees. Finally, I would like to draw your attention to additional sources of information, including application examples that you can download from the Internet. Mettler Toledo publishes articles on thermal analysis and applications from different fields twice per year in their TA User Comms, the well-known Mettler Toledo Technical Customer Magazine. Back issues can be downloaded for free as PDFs at www.mt.com/TA-usercoms as shown on the slide. Our Collected Applications and Thermal Analysis in Practice handbooks contain many other examples and are highly recommended for further reading. In addition, you can access webinars, application handbooks, or information of a more general nature from the internet addresses given on this slide, ensuring that you are always fully up to date in thermal analysis. This concludes my presentation on materials characterization by thermal analysis. Thank you very much for your interest and attention.